Close your eyes and imagine standing beneath a starlit sky. The darkness above is punctuated by countless points of light, each one a sun, a galaxy, a reminder of how vast our cosmos truly is. But as you gaze upward, a question emerges from the silence. What lies beyond the edge of everything we can see? What exists past the boundary of the observable universe? Tonight, we embark on a gentle journey through space and time, exploring the mysteries that dwell at the very limits of existence. Let your mind drift as we contemplate the infinite, the unknowable, and the profound, questions that have captivated humanity since we first looked up at the night sky. The observable universe is the sphere of space from which light has had time to reach us since the beginning of the universe. It is not the entire universe, merely the portion we can detect. Scientists estimate that the observable universe extends approximately 93 billion light-years in diameter. This measurement accounts for the expansion of space itself during the time light has traveled toward us. Why do we question what lies beyond this boundary? Human curiosity drives us to explore beyond every horizon. When we reach the edge of what we know, we cannot help but wonder what secrets hide just beyond our reach. The universe challenges us with a fundamental limit. We cannot see past a certain distance because light from those regions has not yet had time to arrive. The universe is expanding, a discovery that revolutionized our understanding of cosmology. But what does expansion truly mean? Space itself stretches, carrying galaxies away from each other like raisins in rising bread dough. This expansion does not have a center point within our universe. Every location experiences the same phenomenon. Distant galaxies recede from us, and the farther away they are, the faster they appear to move. This expansion creates a paradox. As space stretches, some regions move away from us faster than light can travel through space. These regions cross beyond our cosmic horizon, disappearing from view forever. The universe we can observe represents only a small fraction of what might exist beyond. The structure of our universe contains boundaries defined by the flow of information and light. The particle horizon marks the maximum distance from which particles could have traveled to reach us since the beginning of time. It represents the theoretical limit of the observable universe, shaped by the finite age of the cosmos and the speed of light. The event horizon in cosmology differs from the one surrounding black holes. In the context of the expanding universe, the cosmological event horizon defines the boundary beyond which events cannot ever affect us, no matter how long we wait. As the universe expands, this horizon actually moves closer in physical distance, even as space continues to stretch. The Hubble horizon represents the distance at which objects recede from us at the speed of light due to the expansion of space. Beyond this boundary, the expansion of space carries objects away faster than light can approach us through that expanding space. These horizons shift and evolve as the universe ages and its expansion rate changes. When we observe distant stars and galaxies, we see them as they were in the past, not as they exist today. Light travels at a finite speed, approximately 300,000 kilometers per second. A star 100 light-years away appears as it existed 100 years ago. The light we see departed that star a century before reaching our eyes. This means our view of the universe is inherently historical. The farther we look into space, the deeper we peer into the past. The most distant galaxies visible to our telescopes show us the universe as it appeared billions of years ago, when these galaxies were young and the cosmos itself was in its infancy. The cosmic microwave background radiation provides our oldest view of the universe. This faint glow permeates all of space, a remnant from a time when the universe was only 380,000 years old. At that moment, the cosmos cooled enough for electrons and protons to combine into neutral hydrogen atoms, allowing light to travel freely through space for the first time. This light has been traveling through the expanding universe ever since, stretched by the expansion into microwave wavelengths. The cosmic microwave background forms a sphere around us, marking the farthest we can see using light. Before this point, the universe was opaque, filled with a hot plasma that scattered photons in every direction. The discovery of the cosmic microwave background in 1965 provided compelling evidence for the Big Bang theory. Scientists Arno Penzias and Robert Wilson detected this unexpected microwave radiation coming from every direction in the sky. Their discovery matched predictions made by cosmologists who theorized that the early universe should have been extremely hot and dense. The temperature of the cosmic microwave background is remarkably uniform, approximately 2.7 degrees above absolute zero. However, tiny fluctuations in this temperature, variations of only a few millionths of a degree, reveal the seeds of all structure in the universe. Regions that were slightly denser in the early universe eventually collapsed under gravity to form galaxies, stars, and planets. By studying the cosmic microwave background, scientists discovered crucial information about dark matter and dark energy. The pattern of temperature fluctuations depends on the composition of the universe. Approximately 68% of the universe consists of dark energy, a mysterious force driving the accelerated expansion of space. About 27% is dark matter, invisible matter that interacts gravitationally but does not emit light. Ordinary matter, the atoms that form stars, planets, and our bodies, comprises only about 5% of the total. These proportions emerged from careful analysis of the cosmic microwave background radiation. The size and distribution of hot and cold spots in this ancient light depend on how much matter and energy filled the early universe. By mapping these patterns with increasing precision, cosmologists have refined our understanding of the universe's composition and history. To explore beyond the cosmic horizon defined by light, scientists seek other messengers. Neutrinos are nearly massless particles that rarely interact with matter. Trillions of neutrinos pass through your body every second without leaving a trace. Because they interact so weakly, neutrinos can escape from regions where light cannot, carrying information from the cores of stars and from the earliest moments after the Big Bang. High-energy neutrinos from distant cosmic events travel across the universe, passing through galaxies and clouds of gas without being absorbed or scattered. By detecting these elusive particles, scientists can learn about processes occurring in regions hidden from telescopes. Neutrino astronomy opens a window to environments too dense or energetic for light to escape. Gravitational waves represent another revolutionary tool for exploring the unseen universe. These ripples in space-time itself travel at the speed of light, carrying information about massive cosmic events. When two black holes spiral together and merge, they create gravitational waves that spread across the universe like ripples on a pond. Detectors on Earth can measure these infinitesimal distortions in space-time, revealing collisions that occurred billions of years ago. Unlike light, gravitational waves pass through matter without being absorbed or scattered. They could potentially carry information from the very earliest moments of the Big Bang, before the universe became transparent to light. Future gravitational wave observatories may detect signals from the moment of cosmic inflation, when the universe expanded exponentially in the first fraction of a second after its birth. Despite these new tools, significant challenges limit our ability to observe distant galaxies and cosmic structures. The expansion of space stretches light waves, shifting them toward redder wavelengths and diminishing their energy. The most distant galaxies appear extremely faint and red, requiring powerful telescopes and long exposure times to detect. Dust and gas between galaxies can absorb or scatter light, further obscuring our view. Within our own galaxy, the disk of the Milky Way blocks our view of distant objects in certain directions. Radio interference, atmospheric distortion, and the limitations of our instruments all constrain what we can observe. Dark energy represents one of the greatest mysteries in cosmology. This enigmatic force causes the expansion of the universe to accelerate rather than slow down. While gravity pulls matter together, dark energy pushes space itself apart. As the universe ages, dark energy becomes increasingly dominant, overpowering the attractive force of gravity on cosmic scales. The nature of dark energy remains unknown. It might be a property of space itself, a constant energy density that remains the same even as space expands. Or it could be a dynamic field that changes over time. Whatever its true nature, dark energy will determine the ultimate fate of the universe. As expansion continues and accelerates, galaxies will recede from each other at ever-increasing speeds. Galaxies not gravitationally bound into clusters will drift apart, each becoming isolated in an expanding void. Eventually, galaxies beyond, our local group will recede so quickly that their light can no longer reach us. The night sky will gradually empty as distant galaxies disappear beyond our cosmic horizon. Within our local group of galaxies, gravity remains strong enough to resist the expansion. The Milky Way and Andromeda galaxies will eventually merge, forming a single large elliptical galaxy. This collision will occur in approximately 4 billion years, long before the effects of cosmic expansion isolate our local group from the rest of the universe. The long-term consequences of accelerated expansion are profound. In hundreds of billions of years, an observer in our galaxy would see a dark sky, empty except for the stars in our merged local group. The cosmic microwave background will be stretched to such long wavelengths that it becomes undetectable. All evidence of the Big Bang and the larger universe will fade from view. This isolation raises an intriguing possibility. Future civilizations, arising trillions of years from now, might lack the observational evidence needed to discover that they live in an expanding universe born from a Big Bang. The cosmos they observe would appear static, eternal, and limited to their local galaxy. Without the clues we have today, they might never uncover the true history and nature of the universe. Two main scenarios describe the possible end of the universe if expansion continues indefinitely. The heat death scenario predicts that the universe will expand forever, gradually cooling toward absolute zero. Stars will exhaust their fuel and die. Galaxies will fade as no new stars form. Eventually, even black holes will evaporate, leaving a cold, dark, infinitely dispersed collection of fundamental particles. The Big Rip scenario occurs if dark energy strengthens over time, rather than remaining constant. In this case, the expansion rate would increase without limit. First, galaxy clusters would be torn apart, then individual galaxies, then solar systems. Eventually, the accelerating expansion would overcome the forces holding atoms together, ripping apart molecules, atoms, and even atomic nuclei in a final cosmic catastrophe. Current observations suggest that dark energy remains constant, making the heat death more likely than the Big Rip. However, the true nature of dark energy remains uncertain, and our understanding may evolve as observations improve. Our own sun faces a transformation that will profoundly affect Earth. In approximately 5 billion years, the sun will exhaust the hydrogen fuel in its core. It will swell into a red giant star, expanding beyond the orbit of Mercury and possibly Venus. The sun's outer layers may engulf Earth, or at minimum, intense heat will vaporize our oceans and atmosphere, leaving a scorched, lifeless rock. After its red giant phase, the sun will shed its outer layers, creating a beautiful planetary nebula. The core will collapse into a white dwarf, a dense remnant about the size of Earth but containing approximately half the sun's current mass. This white dwarf will slowly cool over trillions of years, gradually fading from white hot to red, then eventually becoming a black dwarf. Black dwarfs represent the final stage of stellar evolution for low and medium mass stars. These theoretical objects have never been observed because the universe is not yet old enough for any white dwarf to have cooled completely. A black dwarf is simply a white dwarf that has cooled until it no longer emits significant light or heat, a cold, dark cinder floating through space. Over unimaginable timescales, measured in trillions upon trillions of years, black dwarfs may undergo further transformations. Quantum tunneling might allow fusion reactions to occur within their crystalline cores, briefly reigniting these long-dead stars. Eventually, if protons are unstable, even black dwarfs will decay into lighter particles and radiation. Black holes, the universe's most extreme objects, also face eventual destruction through a process called Hawking radiation. According to quantum mechanics, particle and antiparticle pairs constantly appear and disappear near the event horizon of a black hole. Occasionally, one particle falls into the black hole while its partner escapes. To an outside observer, the black hole appears to emit radiation and slowly lose mass. The process is extraordinarily slow for large black holes. A black hole with the mass of the Sun would take approximately 10 to the 67th power years to evaporate completely, a timescale vastly longer than the current age of the universe. Supermassive black holes at the centers of galaxies would persist for 10 to the 100 power years or more. Yet given enough time, all black holes will evaporate, leaving behind only a faint whisper of radiation spreading through the expanding void. This marks one possible endpoint for the universe, a state of maximum entropy where no stars shine, no planets orbit, and nothing changes. Time itself becomes meaningless in a universe that has reached its final equilibrium. The universe contains vast regions nearly devoid of galaxies known as cosmic voids. These immense bubbles, hundreds of millions of light years across, contain far fewer galaxies than average. Voids were first discovered in the 1970s during surveys that mapped the distribution of galaxies in 3 dimensions. The Bootes Void, discovered in 1981, spans approximately 330 million light-years in diameter. Within this enormous region, which should contain thousands of galaxies based on the average density of the universe, only about 60 galaxies have been identified. This profound emptiness earned it the nickname the Great Nothing. The Eridanus supervoid is associated with the cold spot, an unusually cold region in the cosmic microwave background radiation. This void stretches across 1 billion light-years and may be the largest structure ever discovered. The cold spot appears about 70 microkelvins colder than its surroundings, a temperature difference that challenges our understanding of how the early universe formed structure. Scientists theorize that cosmic voids play a crucial role in understanding dark energy and the large-scale structure of the universe. Voids form naturally as gravity pulls matter together into filaments and clusters, leaving empty regions behind. However, the existence of such large voids places constraints on cosmological models and may offer clues about how dark energy has influenced structure formation. The relationship between cosmic voids and the cold spot in the cosmic microwave background remains uncertain. One possibility is that photons traveling through the supervoid lose energy due to the integrated Sachs-Wolf effect, a phenomenon related to how expanding voids affect the energy of passing light. However, the magnitude of the cold spot is difficult to explain through this effect alone. Alternative explanations suggest that the cold spot might represent a statistical fluctuation, a rare but naturally occurring cold region in the cosmic microwave background. Another intriguing possibility is that it represents the imprint of another universe that collided with ours in the distant past, though this idea remains highly speculative and lacks supporting evidence. Throughout history, scientists and philosophers have proposed theories about what might lie beyond the observable universe. The oscillating universe theory suggests that the universe undergoes endless cycles of expansion and contraction. In this model, the Big Bang was not the absolute beginning, but rather the latest in an infinite series of cosmic bounces. According to this theory, the universe expands for billions of years, then gravity eventually overcomes the expansion, causing everything to collapse back into an infinitely dense point. This big crunch would trigger another Big Bang, initiating a new cycle of expansion. The oscillating universe offers an elegant solution to the question of what came before the Big Bang: another universe contracting toward its end. However, current observations suggest that the universe's expansion is accelerating rather than slowing down, making a big crunch unlikely unless dark energy somehow reverses its behavior in the distant future. Without a mechanism to halt and reverse the expansion, the oscillating universe remains an appealing idea, but one not supported by current evidence. The multiverse theory proposes that our universe is just one of countless universes existing in a vast multiverse. Different versions of this theory suggest different mechanisms for generating multiple universes. In eternal inflation, quantum fluctuations during the inflationary period create bubble universes within an ever-expanding superspace. Each bubble universe has its own physical laws and constants, isolated from all others. In the many worlds interpretation of quantum mechanics, every quantum measurement causes the universe to split into multiple branches, each representing a different outcome. This creates an ever-proliferating tree of parallel universes, each as real as our own. In this view, every possible outcome of every quantum event actually occurs in some branch of the multiverse. String theory, which attempts to unify quantum mechanics and general relativity, suggests the existence of additional spatial dimensions beyond the three we experience. These extra dimensions might be compactified, curled up so small that we cannot detect them directly. Different configurations of these hidden dimensions could give rise to universes with different physical properties. The no-boundary proposal, developed by Stephen Hawking and James Hartle, offers a different perspective on cosmic origins. In the Etoile, this model, time itself has a beginning, but there is no initial boundary or singularity. Instead, time becomes indistinguishable from space in the earliest moments. Asking what happened before the Big Bang becomes meaningless, like asking what lies north of the North Pole. In the no-boundary proposal, the universe has finite age, but no sharp beginning point. Time emerges gradually from a state where space and time are intermixed. This approach attempts to eliminate the singularity at the start of the Big Bang, replacing it with a smooth origin governed by quantum mechanics. Quantum fluctuations may have played a crucial role in the birth of our universe. According to quantum mechanics, empty space is not truly empty, but seethes with virtual particles that appear and disappear. Some theories suggest that our universe originated as a quantum fluctuation, a bubble of space and time that spontaneously emerged from nothing. This concept relies on the idea that the total energy of the universe might be zero. The positive energy contained in matter and radiation is balanced by the negative gravitational potential energy. If the sum equals zero, then creating a universe does not violate conservation of energy. A quantum fluctuation could produce space, time, matter, and energy all at once, with the books perfectly balanced. The Big Bounce theory presents an alternative to the traditional Big Bang model. Instead of emerging from a singularity of infinite density, the universe rebounds from a previous contracting phase. In this scenario, the universe undergoes cycles of expansion and contraction, but unlike the oscillating universe, it avoids the singularity problem. Loop quantum gravity, a theoretical framework that applies quantum mechanics to the structure of space-time itself, suggests that quantum effects prevent the universe from collapsing to infinite density. Instead, gravity becomes repulsive at extremely high densities, causing the collapsing universe to bounce back into a new phase of expansion. The Big Bounce replaces the singularity with a smooth transition from contraction to expansion. This model raises fascinating questions about what existed before our universe. If the Big Bounce is correct, Our cosmos emerged from a previous universe that contracted and rebounded. The matter and energy in our universe might be recycled from that earlier incarnation, processed through the extreme conditions of the bounce. Information from the previous universe might be partially preserved or completely erased, depending on the details of the bounce mechanism. As we contemplate the ultimate fate of the universe, we encounter scenarios that challenge our understanding of physics and existence itself. Proton decay, if it occurs, would represent a fundamental transformation of matter. Protons are extraordinarily stable. No experiment has ever observed a proton decaying. However, some theories predict that protons must eventually decay into lighter particles. If protons decay, the timescale would be immense, perhaps 10 to the 35 power years or longer. Over these incomprehensible durations, all ordinary matter would gradually disintegrate. Planets, frozen stellar remnants, and even black dwarfs would dissolve into radiation and lighter particles. The universe would enter a new phase where complex structures cannot exist because the building blocks of matter have ceased to be stable. Another possible ending involves vacuum collapse. Our universe might exist in a false vacuum, a state that appears stable but is not the lowest possible energy state. The true vacuum would have lower energy, but a barrier prevents the transition under normal circumstances. However, quantum tunneling could allow a region of space to spontaneously transition to the true vacuum. This transition would create a bubble of true vacuum that expands at the speed of light, converting the false vacuum to true vacuum as it grows. Inside the bubble, physical laws might be completely different, with different fundamental constants and particle properties. The bubble would spread unstoppably across the universe, destroying everything in its path and replacing it with a new physics that likely could not support the existence of atoms, stars, or life. The terrifying aspect of vacuum collapse is that it would be completely undetectable until the bubble reaches us, traveling at light speed. We would have no warning. One moment the universe would be as it is. The next moment, we would cease to exist as the bubble engulfed us, rewriting the laws of nature. The distinction between true vacuum and false vacuum relates to the energy state of empty space. A true vacuum represents the lowest possible energy state, completely stable with no lower state to decay into. A false vacuum appears stable but exists at a higher energy level than the true ground state. Like a ball resting in a shallow depression on a hillside, it remains in place but could roll downhill to a lower position if disturbed. Scientists debate whether our universe occupies a true vacuum or a false vacuum. The discovery of the Higgs boson and measurements of its mass have allowed physicists to calculate the stability of our vacuum. Current results suggest that we might be in a metastable state. Stable for now, but not the absolute ground state. The lifetime of this metastable vacuum could be many times longer than the current age of the universe, or it could transition at any moment. The uncertainty reflects our incomplete understanding of fundamental physics. A vacuum bubble, should it form, would represent an absolute end for everything in its path. The bubble wall moves at the speed of light through space. Inside, the laws of physics differ fundamentally from those in our universe. Atoms might not form, forces might have different strengths, the speed of light itself might differ. Everything that defines our reality would be erased and replaced with something utterly alien. Yet from a broader perspective, this ending would mark a beginning. The new vacuum state would have its own physics, potentially giving rise to new kinds of structures and complexity we cannot imagine. If consciousness or life could exist in such radically different physics remains an open question, but the possibility cannot be dismissed entirely. Scientists link cosmic evolution to deep philosophical questions about beginnings and endings. The universe appears to have a beginning in the Big Bang, emerging from conditions we struggle to comprehend. It seems destined for an ending, whether through heat death, vacuum collapse, or some other mechanism. Yet many of the theories we have explored suggest that endings might transform into new beginnings. The Big Bounce envisions an eternal cycle where contraction leads to expansion. The oscillating universe similarly proposes endless repetition. The multiverse suggests that new universes continuously emerge, each with its own beginning and fate. Even in scenarios where our universe truly ends, the quantum vacuum might spontaneously create new universes elsewhere in the multiverse. This possibility offers a kind of cosmic consolation. While our specific universe, with its galaxies, stars, and planets, may be finite in time, the larger multiverse or quantum vacuum might be eternal. Universes may come and go like waves on an infinite ocean, each one a temporary structure arising from and returning to a deeper reality. Many cosmologists find beauty in the idea that the end might be another beginning. This perspective echoes ancient philosophical and spiritual traditions that view existence as cyclical rather than linear. Modern physics, using the language of mathematics and the tools of observation, arrives at conclusions that resonate with these timeless insights. The universe challenges us with paradoxes and mysteries that humble our understanding. We live on a tiny planet orbiting an ordinary star in an average galaxy among billions of galaxies. Our entire observable universe might be an infinitesimal speck within a larger multiverse. Everything we can see or measure represents only a fraction of what exists. Yet within our observable universe, we find extraordinary complexity and beauty. Galaxies spiral in elegant patterns. Stars forge heavy elements in their cores and scatter them through space when they die. Planets form, and on at least one, life emerges, evolves, and eventually develops consciousness capable of pondering these cosmic questions. We exist at a special time in cosmic history. The universe is old enough for stars to have formed and created the elements necessary for life, yet young enough that stars still shine and galaxies remain visible. In the deep future, observers would see a much emptier, darker cosmos, with fewer clues about its origin and evolution. The edge of the observable universe represents not just a physical boundary, but an epistemological one. Beyond this horizon lies a realm we cannot observe with light, cannot measure directly, and can only explore through theory and inference. It reminds us that reality extends beyond our capacity to perceive it, that existence is larger than our observations. What lies beyond the edge of the universe? The answer depends on which theory proves correct. Perhaps an infinite expanse of more galaxies and space, forever beyond our view. Perhaps a multiverse of countless other universes, each with its own physics. Perhaps higher dimensional realms described by string theory. Perhaps the answer is none of these, but something we have not yet imagined. The question itself reveals something profound about human nature. We are creatures who build telescopes to see farther, who devise equations to describe the invisible, who refuse to accept that anything is truly unknowable. The edge of the observable universe is not a wall that stops our inquiry, but a frontier that inspires it. As you drift towards sleep, imagine yourself floating at the edge of the observable universe. At that boundary, where light from the beginning of time is just now arriving. Behind you lies everything we can see. Galaxies, stars, planets, the entire cosmic web of matter and energy. Before you lies the unknown, stretching away into mystery. That boundary is not fixed. As time passes, light from more distant regions reaches us, pushing the edge of the observable universe outward. Yet the accelerating expansion ensures that other regions slip beyond our horizon forever, disappearing into unreachable distance. The universe plays a game of revelation and concealment, showing us new wonders while hiding others beyond recovery. Sleep now, knowing that the universe is vaster than imagination, older than memory, and more mysterious than dreams. We are part of this cosmos, made from atoms forged in stellar furnaces, thinking thoughts that span from the quantum to the infinite. The edge of the universe is the edge of our knowledge, but not the limit of what exists. Tomorrow the sun will rise, that ordinary star that makes life possible. The Earth will turn, carrying us through space at thousands of kilometers per hour. Galaxies will continue their slow dance, moving apart as space expands. And somewhere, perhaps, new universes will bubble into existence, beginning their own journeys through time. The universe does not require our understanding to exist. Stars shone for billions of years before eyes evolved to see them. Galaxies formed and evolved without conscious witnesses. Yet here we are, pieces of the universe that have become aware of themselves, capable of asking questions about origin and fate, meaning and purpose. What is beyond the edge of the universe? Perhaps the question itself is part of the answer. We exist in a cosmos that produces beings capable of wonder, capable of curiosity, capable of looking at the night sky and asking what lies beyond. That capacity for questioning might be as fundamental to the universe as matter and energy, space and time. Let the mystery comfort rather than disturb you. Not everything must be known or understood. Some questions may forever exceed our capacity to answer. The universe keeps its deepest secrets, and we are privileged to live within it, to contemplate it, to be part of its ongoing story. Rest now in the knowledge that you are connected to everything. The atoms in your body were forged in stars that died before the Earth formed. You breathe oxygen created by ancient microbes. You think thoughts enabled by billions of years of evolution. You are not separate from the universe, but an integral part of it. The edge of the observable universe marks the limit of what we can see, but not the limit of what we can imagine, theorize, or wonder about. Science proceeds by pushing against boundaries, by testing ideas against observations, by refusing to accept that we have found all the answers. The vastness of space surrounds us with silence. As we drift deeper into contemplation, let us explore the tools humanity has created to peer into the cosmic depths, seeking answers to questions that stir in the quiet moments before sleep. How can neutrinos help us learn about regions beyond the cosmic horizon? These ghostly particles offer a unique window into the universe's hidden realms. Unlike photons, which scatter and absorb when passing through matter, neutrinos slip through obstacles as if they were not there. A neutrino could pass through a light year of solid lead with barely any chance of interaction. This property makes neutrinos extraordinary cosmic messengers. They escape from the cores of collapsing supernovae, carrying information about conditions no telescope can observe. They stream from the sun's center, where nuclear fusion occurs, providing direct evidence of processes hidden beneath the solar surface. They arrive from distant galaxies, bearing witness to violent events in their cores. Neutrino observatories exist deep underground or beneath ice sheets to shield detectors from cosmic rays and other interference. When a neutrino occasionally interacts with an atom in the detector, it produces a flash of light or a charged particle that instruments can record. By analyzing these rare interactions, scientists reconstruct the direction and energy of incoming neutrinos. The IceCube Neutrino Observatory in Antarctica uses a cubic kilometer of ice as its detector. Thousands of sensors buried deep in the ice watch for the faint flashes produced when high-energy neutrinos interact with ice molecules. IceCube has detected neutrinos from distant blazars, supermassive black holes actively consuming matter in faraway galaxies. Future neutrino telescopes may detect the cosmic neutrino background, a sea of low-energy neutrinos produced in the first seconds after the Big Bang. These relic neutrinos filled the universe even before the cosmic microwave background formed. Detecting them would provide information about the universe at an earlier time than any light-based observation can reach. What role do gravitational waves play in understanding the unseen universe? Einstein predicted these ripples in space-time over a century ago, but they were not directly detected until 2016. The LIGO observatories recorded gravitational waves from two merging black holes, confirming a major prediction of general relativity and opening a new window on the cosmos. Gravitational waves carry information encoded in the stretching and squeezing of space-time itself. When massive objects accelerate, they create these waves that propagate outward at light speed. The waves are extraordinarily weak. Even the merger of black holes, each containing dozens of solar masses, produces distortions that stretch space by less than the width of a proton over distances of kilometers. Detecting such tiny distortions requires extraordinary precision. LIGO uses laser interferometry to measure distance changes between mirrors suspended 4 kilometers apart. When a gravitational wave passes through the detector, it alternately stretches space in one direction, while compressing it perpendicular to that direction. This creates a characteristic pattern in the laser interference. Since that first detection, observatories have recorded dozens of gravitational wave events. Most involve merging black holes, but scientists have also detected neutron star mergers. When two neutron stars spiral together and collide, they produce both gravitational waves and a brilliant electromagnetic display spanning gamma rays, optical light, and radio waves. These multi-messenger observations, combining gravitational waves and light, provide unprecedented insights into cosmic catastrophes. The neutron star merger detected in 2017, designated GW170817, allowed astronomers to observe the creation of heavy elements like gold and platinum. The event also provided a new way to measure the expansion rate of the universe. Future gravitational wave observatories will probe even deeper into cosmic history. Space-based detectors like the proposed Laser Interferometer Space Antenna could detect gravitational waves from supermassive black hole mergers across the visible universe. These observatories might even detect primordial gravitational waves from cosmic inflation, a signal from 10 to the negative 35 seconds after the Big Bang. What challenges limit our observation of distant galaxies? As we look deeper into space and further back in time, multiple obstacles obscure our view. The expansion of the universe stretches light from distant galaxies to longer, redder wavelengths. This cosmological redshift dims the light and shifts it out of the visible spectrum into infrared wavelengths. The most distant galaxies known have redshifts greater than 10, meaning their light has been stretched to more than 11 times its original wavelength. Light emitted as ultraviolet radiation arrives at Earth as infrared. Observing these distant objects requires telescopes sensitive to infrared wavelengths, like the James Webb Space Telescope. Intergalactic space is not perfectly transparent. Neutral hydrogen gas between galaxies absorbs ultraviolet light, creating what astronomers call the Lyman alpha forest. This absorption carves numerous dark lines into the spectra of distant quasars. For the most distant objects, this absorption becomes so severe that virtually all light at wavelengths shorter than 121 nanometers is removed. Within our own galaxy, dust lanes block our view in certain directions, creating dark patches in the night sky. Interstellar dust absorbs and scatters starlight, making distant objects appear dimmer and redder. This extinction becomes significant when looking through the disk of the Milky Way toward the galactic center or beyond. Even with perfect instruments and clear lines of sight, the finite speed of light imposes a fundamental limit. Light from the most distant observable objects has been traveling for over 13 billion years. These galaxies appear as they were in the early universe, small and irregular, filled with young blue stars. Their current appearance remains unknown, hidden by the time light takes to cross cosmic distances. Atmospheric turbulence distorts light from celestial objects, causing the twinkling of stars and blurring images of galaxies. Ground-based telescopes use adaptive optics systems to compensate for atmospheric distortion, but these systems work imperfectly and only over small fields of view. Space telescopes avoid atmospheric interference entirely, but face other challenges, including cost, limited size, and the inability to repair or upgrade after launch. The faintness of distant objects demands long exposure times. Capturing sufficient light to analyze the spectrum of a galaxy 13 billion light-years away may require hours or days of telescope time. Competition for access to major observatories is fierce, and observing the most distant objects requires allocating scarce resources. How does dark energy influence the universe's expansion? This mysterious component dominates the cosmic energy budget, comprising approximately 68% of everything in the universe. Yet its nature remains one of physics' greatest puzzles. Dark energy appears to be a property of space itself, remaining constant in density even as space expands. Imagine a box containing 1 cubic meter of space. As the universe expands, this box grows larger, doubling in each dimension to contain 8 cubic meters. The amount of matter inside spreads out, so matter density decreases by a factor of 8. Radiation energy density decreases even faster because expansion stretches wavelengths, reducing photon energy. But dark energy density remains constant. Each cubic meter of new space contains the same amount of dark energy as before. This property causes dark energy to become increasingly dominant as the universe expands. In the early universe, matter density was much higher, and gravity effectively resisted expansion. As space expanded and matter density decreased, dark energy's influence grew. Approximately 5 billion years ago, dark energy became dominant, and the universe's expansion began accelerating. The acceleration means that distant galaxies recede from us at speeds that increase over time. A galaxy currently moving away at 10,000 kilometers per second will be moving away faster in the future, not because anything pushes it, but because the space between us grows at an accelerating rate. This expansion occurs on the largest scales, between galaxy clusters that are not bound together by gravity. Dark energy's influence has profound implications. It determines not only the expansion rate, but also the ultimate fate of the universe. If dark energy remains constant, as current observations suggest, the universe will expand forever, cooling and diluting until reaching a state of maximum entropy called heat death. Several theories attempt to explain dark energy. The cosmological constant, first introduced by Einstein, represents dark energy as an intrinsic property of empty space, a fixed energy density that never changes. This explanation fits observations, but raises troubling questions about why the cosmological constant has its observed value rather than being vastly larger or smaller. Quintessence. Models propose that dark energy is a dynamic field that can change over time. The density of this field might increase or decrease as the universe evolves, leading to different expansion histories and futures than the cosmological constant predicts. Current observations cannot distinguish between a true cosmological constant and slowly varying quintessence. Modified gravity theories offer another approach, suggesting that our understanding of gravity on cosmic scales is incomplete. Perhaps general relativity requires modification at the largest distances. These theories attempt to explain the accelerating expansion without invoking dark energy, instead attributing it to new gravitational physics. So far, modified gravity models struggle to match all observations as successfully as dark energy models do. What will happen to galaxies as expansion continues? Over the next 100 billion years, galaxies not gravitationally bound to our local group will disappear beyond the cosmic horizon. The space between us and distant galaxies will expand faster than light can travel through it, carrying those galaxies out of view forever. The observable universe will shrink, even as the actual universe continues expanding. Within gravitationally bound structures like galaxy clusters, expansion has little effect. The Milky Way and the Andromeda Galaxy are moving toward each other at approximately 120 kilometers per second. In about 4 billion years, they will collide and merge. The collision will be spectacular, with close encounters between billions of stars, but actual stellar collisions will be rare because stars are tiny compared to the distances between them. The merged galaxy, sometimes called Milkomeda or Milkdromeda, will be a large elliptical galaxy. Our solar system will likely be flung into a different orbit, possibly farther from the galactic center. The night sky will be unrecognizable, filled with stars from both galaxies scattered into new patterns. If any astronomers exist billions of years hence, They will observe a universe containing only their single large galaxy surrounded by empty darkness. The local group of galaxies, including the Milky Way, Andromeda, Triangulum, and several dozen smaller galaxies, is gravitationally bound. These galaxies will eventually merge into a single massive galaxy. The same process will occur in other galaxy clusters. The Virgo cluster, the Coma cluster, and other large assemblages of galaxies will each collapse into single enormous galaxies containing trillions of stars. Between these merged supergalaxies, space will continue expanding, increasing the distances to unimaginable scales. Any light traveling between these isolated structures will be stretched to such long wavelengths that it becomes effectively undetectable. The universe will fragment into causally disconnected regions, each containing a single supergalaxy or cluster remnant, alone in an expanding void. What are the long-term consequences of accelerated expansion? As billions of years pass, the effects become increasingly dramatic. New star formation will gradually cease as galaxies exhaust their supplies of cold gas. The bright blue stars that dominate young galaxies have short lifetimes, quickly exhausting their fuel. Over time, these massive stars will die, leaving behind neutron stars and black holes. Medium-mass stars like the Sun will evolve more slowly, shining for billions of years before swelling into red giants and eventually shedding their outer layers. They will leave behind white dwarfs, dense stellar cores that cool slowly over trillions of years. The smallest red dwarf stars burn so slowly that they will shine for tens of trillions of years, far longer than the current age of the universe. Eventually, every galaxy will fade as star formation ceases and existing stars exhaust their fuel. 100 trillion years from now, the galaxies will be filled with white dwarfs, neutron stars, and black holes. Occasional flashes will occur when two white dwarfs collide, or when a white dwarf accretes material from a companion. But these events will become increasingly rare. The cosmic microwave background radiation will be stretched to such long wavelengths that its temperature approaches absolute zero. Its photons will be spread so thin that they become nearly impossible to detect. Any observer in this distant era would see a cold, dark universe, with no evidence of the Big Bang or the existence of other galaxies. What is meant by heat death and Big Rip scenarios? These represent two possible ultimate fates for an eternally expanding universe. Heat death, also called the Big Freeze, occurs if the universe expands forever, while dark energy remains constant or weakens over time. In this scenario, the universe approaches a state of maximum entropy, where all energy has been evenly distributed and no work can be performed. Entropy measures disorder, or the number of possible arrangements of a system. The second law of thermodynamics states that entropy always increases in a closed system. The universe as a whole appears to be a closed system, so its total entropy must increase over time. Stars convert concentrated hydrogen fuel into dispersed heat and light, increasing entropy. Black holes represent states of extremely high entropy, and their eventual evaporation disperses that entropy throughout space. In the heat death scenario, after all stars have died and all black holes have evaporated, the universe will contain only a thin soup of photons, neutrinos, and electrons, all at nearly the same temperature approaching absolute zero. No energy gradients will exist to drive processes or enable complexity. Time will lose meaning because nothing changes. This represents the ultimate end of a universe dominated by entropy. The Big Rip scenario occurs if dark energy strengthens over time rather than remaining constant. In this case, the expansion rate would increase without bound, eventually overcoming all forces that hold structures together. The scenario unfolds in stages, each more dramatic than the last. First, galaxy clusters would be torn apart as the space between galaxies expands faster than gravity can hold them together. Then individual galaxies would dissolve as stars are ripped away from galactic centers. Solar systems would disintegrate as planets are torn from their orbits. Eventually, the expansion would overcome the electromagnetic forces holding molecules together, then the nuclear forces binding atoms. In the final moments before the Big Rip, even atomic nuclei would be torn apart. Protons and neutrons shredded into quarks and gluons. Space-time itself might be destroyed, ripped into disconnected fragments. The Big Rip would represent a true end to everything. Not a slow fade into darkness, but a violent catastrophe occurring at a specific moment in time. Current observations suggest the Big Rip is unlikely. Measurements of dark energy's properties indicate it behaves like a cosmological constant, remaining stable rather than strengthening. However, our observations span only a fraction of cosmic history. Dark energy could begin strengthening in the future, though present data show no indication this will occur. What transformations will the Sun and Earth undergo in the distant future? Our star is approximately 4.6 billion years old, middle-aged for a star of its mass. In roughly 5 billion years, the hydrogen fuel in the Sun's core will be exhausted. With no more fusion to support its outer layers against gravity, the core will contract and heat up. As the core contracts, its temperature will rise enough to ignite hydrogen fusion in a shell surrounding the core. This shell burning will produce more energy than the Sun currently generates. The extra energy will cause the Sun's outer layers to expand dramatically. The Sun will swell into a red giant star, its surface cooling to a reddish color while its total energy output increases. The red giant Sun will expand beyond Mercury's current orbit and possibly beyond. Venus. Whether Earth will be engulfed remains uncertain. The Sun will lose mass as it expands, weakening its gravitational pull and allowing Earth's orbit to spiral outward. Calculations suggest Earth might barely escape being swallowed, but the intense heat will have catastrophic consequences regardless. Earth's oceans will boil away entirely. The atmosphere will be stripped off into space. Surface temperatures will rise to thousands of degrees, melting rock and creating a global magma ocean. Any remnant of Earth that survives will be a scorched, lifeless sphere of molten rock and metal. All evidence of our civilization, all traces of the billions of years of life that evolved here will be erased. After approximately 1 billion years as a red giant, the Sun will exhaust the helium in its core. It will undergo further instabilities, pulsing and shedding its outer layers in a series of thermal pulses. These ejected layers will form a planetary nebula, a beautiful glowing shell of gas expanding into space. At the center will remain the Sun's core, compressed to a sphere about the size of Earth. This stellar remnant is a white dwarf with approximately half the Sun's current mass compressed into Earth's volume. A teaspoon of white dwarf material would weigh several tons. The white dwarf will be incredibly hot initially, with surface temperatures exceeding 100,000 degrees. It will shine with a brilliant blue-white light, but with no fusion reactions to generate new energy, it will gradually cool. What will happen to stars and galaxies over trillions of years? The process that will transform our Sun will eventually affect all similar stars. More massive stars will evolve faster, some exploding as supernovae and leaving behind neutron stars or black holes. Less massive stars will evolve more slowly, with the smallest red dwarf shining for tens of trillions of years. Star formation will gradually cease as galaxies exhaust their cold gas supplies. Each generation of stars recycles some material back into space when they die, but much material becomes locked away in white dwarfs, neutron stars, and black holes. Over time, less and less gas remains available to form new stars. The last stars will form approximately 100 trillion years from now. After star formation ceases, the universe enters what astronomers call the degenerate era, dominated by stellar remnants. White dwarfs will cool slowly, fading from blue-white to red to brown to black. Neutron stars, already cooled to near background temperature, will continue their solitary existence. Black holes will slowly accrete any nearby matter while radiating energy through Hawking radiation. Occasionally, white dwarfs or neutron stars will collide, briefly illuminating their galaxies with brilliant flashes. Brown dwarfs, failed stars too small to sustain fusion, will slowly cool. Planets will be ejected from their orbits through gravitational interactions with passing stars. while others will spiral into their stellar remnants through dynamical friction. Over timescales of 10 to the 15 to 10 to the 20 years, galaxies themselves will evaporate. Stars will occasionally gain enough energy from gravitational encounters to escape their galaxies entirely. Others will lose energy and spiral inward toward the supermassive black holes at galactic centers. Eventually, galaxies will dissolve, leaving most of their stars scattered through intergalactic space, while the rest have been consumed by central black holes. What are black dwarfs and their role in the universe's final phase? Black dwarfs are the theoretical endpoint of white dwarf evolution. As white dwarfs radiate away their heat over trillions of years, they will eventually cool to the temperature of the cosmic microwave background, then continue cooling as the background radiation itself cools due to cosmic expansion. A black dwarf is simply a white dwarf that has cooled completely, no longer emitting significant light or heat. These objects have never been observed because the universe is not old enough for any white dwarf to have completed this transformation. The coolest white dwarfs discovered are still thousands of degrees above the temperature that would qualify them as black dwarfs. Black dwarfs will be composed primarily of carbon and oxygen. Arranged in a crystalline lattice, they will be dark, cold, and incredibly dense, with surface gravity thousands of times stronger than Earth's. A black dwarf might persist unchanged for an almost incomprehensible duration, a monument to a star that died trillions of years earlier. However, even black dwarfs may not be eternal. On timescales of 10 to the 32 years, quantum tunneling might allow fusion reactions to occur within their cold cores. Carbon nuclei could tunnel through the quantum barriers that normally prevent fusion at low temperatures, slowly transmuting the black dwarf's interior. These reactions would release small amounts of energy, causing the black dwarf to glow faintly once more before the fuel is exhausted. If protons are unstable, as some theories of particle physics predict, black dwarfs will eventually decay. Proton decay has never been observed, and experiments have placed the proton lifetime at greater than 10 to the 34 years. But if protons do decay, even on much longer timescales, black dwarfs will slowly disintegrate into lighter particles and radiation. The atoms that once formed stars and planets will cease to exist, breaking down into photons, neutrinos, and whatever other stable particles remain. How does Hawking radiation lead to the evaporation of black holes? Stephen Hawking discovered in 1974 that black holes are not perfectly black. Quantum effects near the event horizon cause black holes to emit radiation and slowly lose mass. This prediction combined general relativity, quantum mechanics, and thermodynamics in an unexpected way. The quantum vacuum is never truly empty, but constantly produces pairs of virtual particles and antiparticles. These pairs normally annihilate each other almost instantly. However, near a black hole's event horizon, one particle might fall into the black hole while its partner escapes. To an outside observer, the black hole appears to emit a particle. Conservation of energy requires that the black hole lose a small amount of mass to account for the escaping particle's energy. The temperature of Hawking radiation is inversely proportional to the black hole's mass. Stellar mass black holes have temperatures of only a few billionths of a degree above absolute zero, far colder than the cosmic microwave background. These black holes actually grow by absorbing background radiation faster than they emit Hawking radiation. Only when the universe has expanded and cooled sufficiently will Hawking radiation dominate. Supermassive black holes, containing millions or billions of solar masses, have even lower Hawking temperatures. A black hole with a billion solar masses has a temperature of approximately 10 to the -17th power degrees, incredibly close to absolute zero. The timescale for such a black hole to evaporate through Hawking radiation is approximately 10 to the 100 power years, a duration with no name, incomprehensibly longer than the current age of the universe. As a black hole loses mass through Hawking radiation, its temperature increases and it evaporates faster. The process accelerates, with the final moments of evaporation releasing a burst of high-energy particles and radiation. The very last instant, when the black hole finally disappears entirely, remains mysterious because it requires a theory of quantum gravity that we do not yet possess. After all black holes have evaporated, the universe will enter its final era. No stars will remain, no planets, no complex structures of any kind. Only a dilute gas of photons, neutrinos, electrons, and positrons will fill the ever-expanding void. The temperature will approach absolute zero. Entropy will reach its maximum. Nothing will happen because there will be nothing left that can happen. Time itself will become meaningless in a universe that has reached its final equilibrium state. What are cosmic voids, and how were they first discovered? The universe's matter is not distributed uniformly, but arranged in an immense cosmic web. Galaxy clusters form dense nodes connected by filaments of galaxies and dark matter. Between these structures lie vast regions containing very few galaxies, known as cosmic voids. Voids were first discovered in the late 1970s during redshift surveys that mapped galaxies in 3 dimensions. Astronomers measured the redshifts of thousands of galaxies to determine their distances, creating 3-dimensional maps of cosmic structure. These maps revealed surprising patterns. Galaxies clustered along filaments and sheets surrounding enormous, empty regions. The discovery challenged expectations. If matter were distributed smoothly with random variations, voids would be rare and small. Instead, voids were common and huge, often spanning hundreds of millions of light-years. This suggested that the distribution of matter in the universe follows specific patterns arising from cosmic structure formation. Voids form naturally as gravity amplifies density variations in the early universe. Regions slightly denser than average attract more matter through gravity, growing denser still. This leaves surrounding regions depleted of matter. Over billions of years, this process creates the cosmic web structure we observe today with matter, concentrated into filaments and clusters, while voids expand and become increasingly empty. Some voids are larger and emptier than expected, challenging our understanding of structure formation. These supervoids might provide clues about dark energy and the expansion history of the universe. The distribution and properties of voids constrain cosmological models because their formation depends on the balance between gravity pulling matter together and cosmic expansion pulling it apart. What makes the Bootes void and Eridanus supervoid special? The Bootes void, discovered in 1981 by Robert Kirshner and colleagues, was one of the first large voids identified. It spans approximately 330 million light-years in diameter, centered about 700 million light-years from Earth. Within this enormous region, only about 60 galaxies have been found, compared to thousands that would be expected based on average galaxy density. The relative emptiness of the Bootes void earned it nicknames like the Great Nothing and the Great Void. Its discovery raised questions about structure formation in the early universe. How could such a large region become so underdense? Did something prevent galaxies from forming there? Or did galaxies form but later migrate out of the void into surrounding denser regions? Studies of the Bootes void revealed that it is not completely empty. The galaxies within it appear normal, similar to galaxies in average density regions. The void likely formed through gravitational processes, with matter slowly flowing out over billions of years as it was pulled toward denser regions. The void continues to expand as the universe expands, becoming increasingly empty over time. The Eridanus supervoid represents an even more extreme structure. This immense underdense region spans approximately 1 billion light-years and lies about 3 billion light-years from Earth. Its significance extends beyond its size, as it may be connected to one of the most puzzling features of the cosmic microwave background radiation. The cold spot in the cosmic microwave background is an unusually large cold region in the sky, approximately 70 microkelvins colder than its surroundings and spanning about 5 degrees across. Random fluctuations in the cosmic microwave background cannot easily explain a cold region this large and this cold. The probability of such a feature arising by chance is very small, leading astronomers to search for alternative explanations. The Eridanus supervoid's alignment with the cold spot suggests a possible connection. One hypothesis involves the integrated Sachs-Wolfe effect, which predicts that photons traveling through expanding voids should lose energy. As photons enter a void, they climb out of a gravitational potential well, losing energy and shifting to longer wavelengths. If the void expands while photons cross it, they gain less energy, falling back into the potential well than they lost climbing out, resulting in a net energy loss. This effect could cause photons from the cosmic microwave background passing through the Eridanus supervoid to appear colder than surrounding regions. However, calculations suggest that even this enormous void cannot fully explain the magnitude of the cold spot. The observed temperature deficit is larger than the integrated Sachs-Wolfe effect alone can produce, leaving the cold spot partially unexplained. How might voids be connected to dark energy and the structure of the universe? Voids provide a unique laboratory for studying dark energy's effects. Within voids, matter density is very low, so dark energy's influence becomes relatively more important. The expansion rate within voids differs from that in average density regions, potentially offering clues about dark energy's properties. Some cosmologists have proposed that voids themselves might influence cosmic expansion through the Lemaitre-Tolman-Bondy model, which allows for local variations in expansion rate. If we happen to live near the center of an enormous underdense region, the faster expansion there could mimic the effects of dark energy. However, observations of the cosmic microwave background and galaxy distributions constrain how underdense our local region can be, making this explanation unlikely. The number, size, and distribution of voids depend on cosmological parameters, including dark energy's strength, the amount of matter in the universe, and the amplitude of density fluctuations in the early universe. By surveying voids and measuring their properties, astronomers can constrain these parameters independently of other methods. Voids thus serve as complementary probes of cosmology. Voids also affect galaxy evolution. Galaxies in voids experience fewer interactions and mergers than galaxies in denser environments. They tend to be smaller, bluer, and more gas-rich, forming stars more slowly. Studying void galaxies provides insights into how environment influences galaxy properties, helping disentangle nature versus nurture in cosmic structure formation. What is the relationship between cosmic voids and the cold spot in the cosmic microwave background? This question remains partially unresolved, representing an active area of research in cosmology. The alignment of the Eridanus supervoid with the cold spot is intriguing, but may be coincidental. Multiple factors could contribute to the cold spot's existence. One possibility is that the cold spot represents a rare but natural statistical fluctuation in the cosmic microwave background. The cosmic microwave background contains approximately 12 million resolution elements across the sky. With this many independent regions, we expect to see some unusual features simply by chance. The cold spot might be the most extreme example in our observable sky, unlikely in any particular location, but probable somewhere. Another hypothesis suggests that the cold spot could be evidence of a cosmic texture, a topological defect in space-time predicted by some theories of the early universe. Textures form when symmetries break during phase transitions in the very early universe. They would leave distinctive imprints in the cosmic microwave background, including cold spots. However, textures should also produce characteristic patterns in microwave background polarization, which have not been observed. More speculatively, Some physicists have proposed that the cold spot might represent the imprint of another universe that collided with ours in the distant past. In multiverse theories involving eternal inflation, bubble universes can form and occasionally collide. A collision would leave a circular imprint in the cosmic microwave background, potentially appearing as a cold or hot spot. However, this hypothesis remains highly speculative and difficult to test. The most likely explanation combines the Eridanus supervoid's integrated Sachs-Wolf effect with statistical fluctuation. The supervoid may contribute to the cold spot's temperature deficit, while random chance accounts for the additional coldness. This explanation requires no new physics, merely acknowledging that rare events do occur in a large dataset. Future observations with improved cosmic microwave background experiments and deeper galaxy surveys will help resolve this mystery. By mapping the three-dimensional distribution of matter more completely, astronomers can better calculate the expected temperature shift from all structures along the line of sight to the cold spot. This will determine whether known structures suffice to explain it or whether additional mechanisms must be invoked. What is the oscillating universe theory, also known as the Big Bang Big Crunch cycle? This elegant idea proposes that the universe undergoes endless cycles of expansion and contraction. Each cycle begins with a Big Bang, expands for billions of years, then eventually collapses back to a big crunch. The crunch transitions into a new Big Bang, initiating another cycle of expansion. In this model, time is infinite in both directions. There was no first Big Bang, no absolute beginning. Every cycle is preceded by another and followed by another, extending forever into past and future. The universe is eternal, even though any particular cycle has finite duration. Questions about what caused the Big Bang, or what came before it, are answered simply. The previous universe, collapsing toward its end. The oscillating universe theory offers philosophical appeal. It avoids the problem of creation, the question of how something came from nothing. It provides a kind of cosmic recycling where matter and energy are reprocessed through each cycle. The universe never truly ends but transforms from one state to another, death and rebirth occurring on a cosmic scale. However, current observations do not support this model. The discovery that cosmic expansion is accelerating rather than decelerating poses a fundamental challenge. If dark energy continues to drive acceleration, the universe will never collapse. Without a mechanism to halt and reverse the expansion, a big crunch cannot occur. The oscillating universe requires either that dark energy eventually reverses its effect, or that some other force eventually overcomes the expansion. Another problem involves entropy. Each cycle would add entropy to the universe, as required by the second law of thermodynamics. If cycles have been occurring eternally, entropy should be infinite, and the universe should be in a state of maximum disorder. The fact that we observe structure and organization suggests either that cycles have not been occurring forever, or that something resets entropy between cycles. Despite these challenges, variants of the oscillating universe continue to attract interest. Some models invoke quantum effects or higher dimensional physics to enable bounces without violating known physics. These neo-oscillatory models differ from the classical picture, but preserve the appealing concept of an eternal, cyclical cosmos. The multiverse concept represents one of the most profound shifts in cosmological thinking. Rather than viewing our universe as all that exists, multiverse theories propose that countless other universes populate a vast cosmic ensemble, each potentially with different laws of physics, different constants of nature, different histories. The multiverse emerges naturally from several independent theoretical frameworks. Eternal inflation, quantum mechanics, string theory, and even the mathematical structure of reality itself all point toward the possible existence of multiple universes. Each framework suggests a different type of multiverse with distinct properties and implications. In eternal inflation, the process that caused our universe to expand exponentially in its first moments never truly ends. While inflation stopped in our local region, allowing matter and energy to form. It continues elsewhere. Quantum fluctuations cause different regions to stop inflating at different times, creating bubble universes within an eternally inflating background space. Each bubble universe is causally disconnected from all others. The space between bubbles expands so rapidly that no signal can travel from one bubble to another. Each bubble is effectively its own universe, with its own Big Bang marking when inflation ended in that region. Our observable universe is just one such bubble, surrounded by an infinite inflating space containing countless other bubble universes. These bubble universes need not have identical physics. During the phase transition that ends inflation in each bubble, symmetries break randomly. The values of fundamental constants, the masses of particles, even which forces exist, might differ from bubble to bubble. Most bubbles would have physics incompatible with life as we know it. Some might have no atoms, no chemistry, no complexity. Others might have richer physics than ours, possibilities we cannot imagine. This leads to what some call the anthropic principle applied to the multiverse. We observe our universe's particular physics not because it is the only possibility, but because universes with different physics cannot produce observers to contemplate them. We find ourselves in a bubble where constants are fine-tuned for complexity because only such bubbles can contain beings asking why constants have their observed values. The quantum multiverse emerges from the many worlds interpretation of quantum mechanics. According to standard quantum theory, particles exist in superpositions of multiple states until measured. The act of measurement causes the wave function to collapse, randomly selecting one outcome. The many worlds interpretation suggests that measurement does not collapse the wave function, but instead causes the universe to split into multiple branches. In this view, every quantum event with multiple possible outcomes actually produces all outcomes, each in a separate branch of reality. When you measure whether a particle spins up or down, the universe splits. In one branch you observe spin up. In another branch, an equally real version of you observes spin down. Both branches continue evolving, completely unaware of each other. This interpretation implies an incomprehensibly vast multiverse constantly branching. Every quantum interaction, from particle decays to neural firings in your brain, creates new branches. The number of universes increases exponentially with each passing moment. All possible outcomes of all quantum events actually occur somewhere in this ever-proliferating tree of parallel realities. Critics argue that the many worlds interpretation is unfalsifiable and violates Occam's razor by proposing countless unobservable universes. Proponents counter that it actually simplifies quantum mechanics by removing the problematic wave function collapse and treating the Schrödinger equation as exactly true at all times. The debate continues, highlighting how our interpretation of quantum mechanics carries profound cosmological implications. String theory suggests yet another type of multiverse. String theory attempts to unify quantum mechanics and gravity by proposing that fundamental particles are not point-like, but tiny vibrating strings. Different vibration patterns correspond to different particles. The theory requires extra spatial dimensions beyond the three we experience. These extra dimensions must be compactified, curled up into tiny shapes too small to detect directly. The remarkable discovery is that many different compactification geometries are mathematically consistent. Each geometry produces different physics in the three large dimensions we inhabit. Different compactifications yield different particles, different forces, different fundamental constants. The number of possible compactifications is staggering, estimated at 10 to the 500 power or more. This vast landscape of possible string theory vacua might all be physically realized. During the Big Bang or cosmic inflation, different regions might settle into different compactifications, creating a patchwork multiverse where physics varies from region to region. This string theory landscape offers another anthropic explanation for fine-tuning. If all possible values of constants are realized somewhere in the multiverse, we naturally find ourselves in a region where constants permit our existence. The apparent fine-tuning of our universe's physics reflects selection bias rather than design. What is the no-boundary proposal by Hawking and Hartley? Stephen Hawking and James Hartley developed this idea in the 1980s as a way to describe the universe's origin without invoking an initial singularity. Their proposal applies quantum mechanics to the universe as a whole, treating the cosmos as a quantum system. In classical general relativity, time runs backward toward the Big Bang and terminates at a singularity where density and temperature become infinite and physics breaks down. The no-boundary proposal suggests that near the Big Bang, time behaves differently. It becomes mixed with space, losing its distinct character. In the earliest moments, the distinction between time and space blurs. Imagine a sphere representing space-time. Near the North Pole, lines of longitude converge. The North Pole itself is not a boundary but merely a point where all directions become equivalent. Similarly, in the no-boundary proposal, the earliest moment of the universe is not a boundary or edge but merely a point where time becomes indistinguishable from space. This means that asking what happened before the Big Bang becomes as meaningless as asking what lies north of the North Pole. There is no before because time itself emerged gradually from a state where temporal direction did not exist. The universe has finite age but no beginning boundary. Time has a starting point but not an edge. The mathematics of the no-boundary proposal requires considering all possible space-time geometries and summing their quantum mechanical contributions. This path integral approach treats space-time itself as a quantum object that can exist in superpositions. The universe's current state emerges from the sum of all possible histories, weighted by their quantum probabilities. This proposal eliminates the singularity problem and provides a self-contained description of cosmic origins. The universe creates itself from nothing through quantum processes, requiring no external cause or prior state. Critics argue that the mathematical framework remains incompletely developed and that competing quantum cosmology proposals exist. Nevertheless, the no-boundary proposal represents a bold attempt to apply quantum mechanics to the biggest question of all. Why does anything exist? What does string theory suggest about higher dimensions and parallel universes? String theory requires additional spatial dimensions beyond the three we experience. The most successful version, called M-theory, requires 11 total dimensions, 10 spatial and 1 temporal. 6 or 7 of these spatial dimensions are compactified, hidden from direct observation. These extra dimensions might be curled up at every point in space, forming tiny geometrical structures called Calabi-Yau manifolds. These shapes are extraordinarily complex, with intricate topologies that determine the physics in the large dimensions. Different Calabi-Yau shapes produce different particle spectra, different force strengths, different cosmological constants. The hidden dimensions might not be tiny everywhere. Some theories propose that extra dimensions are large but hidden because ordinary matter is confined to a three-dimensional membrane, or brane, embedded in the higher dimensional space. We live on a brane and cannot detect the extra dimensions directly because all particles we can produce are also confined to the brane. However, gravity might propagate through all dimensions. This could explain why gravity is so much weaker than other forces. Gravitational field lines spread out into extra dimensions, diluting gravity's strength in our three-dimensional brane. This brane world scenario makes testable predictions about gravity at very short distances and about the production of microscopic black holes in particle accelerators. Parallel brane universes might exist in the extra dimensions, separated from ours by tiny distances in directions we cannot access. These parallel universes would be invisible and unreachable because light and matter cannot leave our brane. Only gravity can propagate between branes. Collisions between branes might trigger big bangs, providing a mechanism for cosmic creation and possibly cyclic cosmology. String theory's landscape of vacua suggests that different regions of a larger multiverse might exist in different vacuum states with different compactifications. Transitions between vacua could occur through quantum tunneling creating bubbles of new vacuum states within existing ones. This produces a fractal multiverse structure with infinite variety. How might quantum fluctuations have led to the birth of our universe? Quantum mechanics allows energy to fluctuate on short timescales due to the Heisenberg uncertainty principle. The more energy borrowed from the vacuum, the shorter the time before it must be repaid. These fluctuations constantly create and destroy virtual particles throughout empty space. On the tiniest scales, space-time itself fluctuates. Quantum foam describes the roiling structure of space-time at the Planck scale, approximately 10 to the negative 35 meters. At this scale, the smooth geometry of space-time breaks down into a churning sea of quantum uncertainty where space and time lose their classical meanings. Some cosmologists propose that our entire universe originated as a quantum fluctuation. The universe might have tunneled from nothing into existence, borrowing energy from the vacuum to create space, time, matter, and energy all at once. If the total energy of the universe equals zero, with positive matter energy balanced by negative gravitational potential energy, then this creation violates no conservation laws. The universe could emerge as a false vacuum bubble, a region where quantum fields settled into a higher energy state than the true ground state. This false vacuum energy would drive cosmic inflation, causing the bubble to expand exponentially. As the universe inflated and cooled, the false vacuum decayed to lower energy states, releasing energy that became the matter and radiation filling space. This quantum creation scenario suggests that universes might appear spontaneously and continuously throughout the multiverse. Quantum fluctuations could produce bubble universes within existing spaces, or even create space itself. Our universe might be one bubble in an infinite quantum foam of appearing and disappearing cosmic bubbles. The mathematical framework for quantum cosmology remains incomplete. Physicists debate how to properly apply quantum mechanics to the universe as a whole. Unlike laboratory systems that interact with environments, the universe has no outside. Standard quantum mechanics assumes an external observer, but cosmology requires a description that works without one. Developing a fully consistent quantum theory of cosmology represents one of physics' greatest challenges. What is the Big Bounce theory, and how does it differ from the Big Bang? The Big Bounce proposes that our universe emerged not from an initial singularity, but from the collapse and rebound of a previous universe. Instead of beginning at a point of infinite density, the universe reached a maximum density and then bounced back into expansion. The key difference from the classical Big Bang is the avoidance of the singularity. General relativity predicts that gravitational collapse leads to singularities where density and curvature become infinite. At these points, physics breaks down and the theory fails. The Big Bounce invokes quantum effects to prevent the singularity, replacing it with a smooth transition from contraction to expansion. Loop quantum gravity, an approach to quantum gravity that treats space-time as composed of discrete quantum units, provides a framework for the Big Bounce. In loop quantum gravity, space has a granular structure at the Planck scale. This discreteness prevents density from becoming infinite during collapse. When matter is compressed to the Planck density, approximately 10 to the 93 power grams per cubic centimeter, quantum gravitational effects become dominant. At these extreme densities, gravity becomes repulsive rather than attractive. This quantum bounce effect causes the collapsing universe to rebound into expansion. The bounce is not instantaneous, but occurs over a brief period when the universe is in a quantum gravitational state. During the bounce, the usual rules of space-time break down and quantum geometry dominates. If the Big Bounce is correct, our universe has a finite age measured from the bounce, but is not the first universe. It emerged from a previous universe that contracted and rebounded. This raises questions about what that previous universe was like and whether information from it survived the bounce. Some models suggest that the bounce preserves certain large-scale features while erasing small-scale details. The overall geometry and expansion might carry through, while quantum fluctuations are refreshed. Other models propose that each bounce randomizes initial conditions, producing a new universe with no memory of its predecessor. The fate of information through the bounce remains an open question. The Big Bounce could be a one-time event or part of an eternal cycle. In cyclic models, universes bounce repeatedly, each cycle lasting hundreds of billions of years. The universe expands, forms structures, ages, then contracts again, reaching the Planck density and bouncing into a new cycle. This provides an eternal cosmology where time extends infinitely into past and future. Current observations cannot distinguish between the Big Bang and Big Bounce scenarios for our universe's origin. Both models fit the observed expansion, cosmic microwave background, and large-scale structure. However, they make different predictions about the very early universe and about the nature of time and causation. Future observations of primordial gravitational waves or detailed features of the cosmic microwave background might provide distinguishing evidence. Could proton decay or vacuum collapse destroy the universe? These represent possible mechanisms for the universe's ultimate destruction, different from the slow fade of heat death. Proton decay would gradually dismantle all matter, while vacuum collapse would destroy the universe suddenly and completely. Protons appear stable, with no confirmed observations of spontaneous decay. However, grand unified theories that attempt to unify the electromagnetic, weak and strong forces predict that protons must eventually decay. The predicted lifetimes vary by theory, but typically exceed 10 to the 34 power years, far longer than current experimental limits. If protons decay, ordinary matter is ultimately unstable. Over vast timescales, every proton in the universe would decay into lighter particles. Neutrons bound in nuclei would decay even faster, since free neutrons decay in about 15 minutes. Atoms would cease to exist as their nuclei disintegrated. This would occur gradually over incomprehensible durations. Long after all stars have died and all black holes evaporated, the cold remnants of planets and stellar cores would slowly dissolve. Each proton decay would release a small flash of energy, the final warmth in a cooling cosmos. Eventually, no complex matter would remain, only a thin gas of electrons, positrons, photons, and neutrinos spreading through expanding space. The universe would lose its last potential for complexity. Without stable protons, no atoms can form, no chemistry can occur, no structures can persist. This marks a final endpoint beyond which nothing interesting can happen. The universe reaches its ultimate simplicity, having decayed away all the building blocks that allowed brief islands of order to exist. Vacuum collapse presents a more dramatic ending. Our universe might exist in a false vacuum, a metastable state that appears stable but is not the lowest possible energy state. Quantum mechanics allows transitions between vacuum states through a process called quantum tunneling. What is a true vacuum versus a false vacuum? Imagine a ball resting in a shallow bowl on a hillside. The ball is stable in its current position, requiring energy to push it out of the bowl, but a deeper valley exists lower on the hillside. If the ball could tunnel through the hill, it would reach a lower energy state. The shallow bowl represents a false vacuum, locally stable but not the global minimum. The deep valley is the true vacuum, the lowest possible energy state. For a quantum field, the false vacuum has higher energy density than the true vacuum. The difference might seem small, but it has enormous consequences. If any region of space tunnels to the true vacuum, it forms a bubble that expands at the speed of light. The bubble wall converts false vacuum to true vacuum as it expands, releasing energy in the process. Inside the bubble, physics is completely different. The new vacuum state has different values for fundamental constants, different particle masses, possibly different forces entirely. Most likely, the new physics cannot support atoms or any structure. Everything inside the bubble is destroyed and replaced with a radically different state. How might a vacuum bubble end the universe at the speed of light? Once formed, the bubble expands inexorably. The bubble wall moves at light speed through space, so there is no warning of its approach. You would not see it coming because the light carrying that information travels at the same speed as the bubble wall itself. The destruction would arrive simultaneously with any signal announcing it. As the bubble wall passes, the vacuum state changes. Particles that were stable become unstable. Forces that held matter together vanish or change strength. Atoms dissolve. Space itself is restructured. Everything within the bubble experiences a complete reset of physical laws. The bubble would not stop expanding. It would continue at light speed, eventually encompassing our entire observable universe and beyond. If our universe is truly in a false vacuum, this catastrophe could occur at any moment. Some region of space, perhaps billions of light years away, might right now be tunneling to the true vacuum, creating a bubble that will eventually reach us. The probability of this occurring depends on how metastable our vacuum is. Measurements of the Higgs boson mass and the top quark mass allow physicists to calculate the stability of our vacuum. Current results suggest we might be in a metastable state. Not quite stable, but with an extremely long expected lifetime, much longer than the current age of the universe. This means vacuum decay is unlikely in the near future, but cannot be ruled out over vast timescales. The universe might persist for 10 to the 100 power years or more before a bubble forms, or a bubble might form tomorrow. The quantum nature of tunneling means we cannot predict when or where it will occur, only calculate probabilities. Some physicists find comfort in anthropic reasoning. If vacuum decay were common, most regions of the multiverse would have decayed long ago. The fact that we exist in a stable vacuum suggests either that our vacuum is genuinely stable or that its lifetime is much longer than typical cosmic timescales. Observers can only exist in regions that remain stable long enough for stars and life to develop. How do scientists link cosmic evolution to philosophical ideas about beginnings and endings? Cosmology touches on questions that have occupied philosophers and theologians for millennia. Why does anything exist? Did the universe have a beginning? Will it have an end? What, if anything, lies beyond or outside the cosmos? Modern cosmology provides scientific frameworks for addressing these questions, while acknowledging limits to knowledge. The Big Bang describes the early universe's evolution from an extremely hot, dense state. But it does not explain what caused that state or whether anything existed before. The theory describes how the universe evolves, but not why it exists. Similarly, cosmology can predict possible futures, from heat death to Big Rip to vacuum collapse, but it cannot tell us which will occur with certainty or whether other possibilities exist. The universe's fate depends on quantities we cannot yet measure with sufficient precision, particularly the nature of dark energy and the stability of our vacuum state. These limits on knowledge are not failures of science, but reflections of reality's structure. Some questions might be unanswerable because they lie beyond what evidence can reach. Others might be meaningless, like asking what happened before time began. Science excels at answering how questions, but often finds why questions elusive or ill-defined. The relationship between science and philosophy becomes especially intimate in cosmology. Scientists make philosophical assumptions when choosing which theories to pursue, how to interpret quantum mechanics, whether to take multiverse theories seriously. Philosophers contribute by analyzing the logical structure of cosmological arguments and clarifying conceptual confusions. The universe's apparent fine-tuning for life raises philosophical debates about explanation and probability. Some see fine-tuning as evidence for design or for the multiverse. Others argue that fine-tuning is an illusion, or that we lack the framework to properly calculate how surprising our universe's properties are. The debate involves both empirical questions about physics and philosophical questions about how to reason under radical uncertainty. Cosmology also informs philosophical debates about the nature of time. Is time fundamental or emergent? Does time have a direction, and if so, why? Can time be circular, allowing closed time-like curves? These questions matter for understanding causation, free will, and the possibility of time travel. Physics and philosophy must work together to make progress. Why do many cosmologists believe the end might be another beginning? Several lines of reasoning support this intriguing possibility. First, cyclic cosmological models like the Big Bounce propose that collapse leads to rebound, making each ending a prelude to a new beginning. If our universe emerged from a previous one, why shouldn't it seed another universe when it ends? Second, quantum mechanics suggests that vacuum states can transition to other vacuum states. If our universe undergoes vacuum decay, the new vacuum state represents a different universe with its own physics. The end of our universe would mark the beginning of something new, even if radically different and inhospitable to life as we know it. Third, the multiverse framework suggests that new universes constantly emerge through various mechanisms. Even if our universe ends, the larger multiverse continues producing new bubble universes through eternal inflation, quantum fluctuations, or brain collisions. The cosmic story continues elsewhere, beginnings occurring while other universes experience their endings. Fourth, black holes might serve as cosmic seeds. Some speculate that the interiors of black holes bud off to become new universes, causally disconnected from the parent universe. In this scenario, the supermassive black holes in galaxy centers are parents to entire new universes. Our universe might itself be the interior of a black hole in a larger parent universe. Finally, the mathematical elegance of eternal cosmologies appeals to many physicists. A universe that has always existed and will always exist, in some form, avoids the puzzle of creation from nothing. Eternal return, whether through precise repetition or infinite variation, suggests that existence itself is the fundamental state, with particular universes being temporary manifestations of an underlying permanence. These ideas remain speculative, but they reflect cosmology's expansion beyond merely describing our observable universe to contemplating the nature of existence itself. The questions reach toward ultimate concerns. Why something rather than nothing? What, if anything, is eternal? Whether existence has inherent meaning or purpose? The scientific method cannot answer these ultimate questions definitively, but it can constrain possibilities and reveal unexpected connections. Observations of the cosmic microwave background inform theories about what preceded the Big Bang. Measurements of dark energy determine which ultimate fate is most likely. Discoveries in particle physics reveal whether our vacuum is stable. As observations improve and theories develop, some questions that seemed purely philosophical become scientifically tractable. Others remain beyond current methods, but might yield to future techniques. Still others might be genuinely unanswerable, reflecting fundamental limits on what beings within a universe can learn about its ultimate context. The possibility that endings are also beginnings offers a kind of cosmic hope. Even if our universe faces an ultimate ending, the larger story might continue. If the multiverse is real, if new universes emerge from old ones, if existence itself is eternal, even while particular configurations come and go, then we are part of an endless cosmic story with no final chapter. This perspective resonates with many spiritual and philosophical traditions that view existence as cyclical or emanating from an eternal source. Modern cosmology, using different language and methods, arrives at remarkably similar possibilities. Whether endings truly are beginnings remains unknown, but the fact that science can seriously entertain such ideas shows how far our understanding has progressed. As you drift towards sleep, consider the profound journey we have taken, from the edge of the observable universe to the possibility of multiverses, from the heat death of the cosmos to the potential for eternal return, from quantum fluctuations to the largest structures in space. The universe reveals itself as more mysterious and more magnificent than our ancestors could have imagined. We live in a special time when human knowledge reaches far enough to glimpse these deep mysteries while acknowledging how much remains unknown. We can measure the age of the universe to remarkable precision while remaining uncertain about its ultimate fate. We can map cosmic structure billions of light years away while speculating about other universes forever beyond our reach. The questions we have explored: what is beyond the edge of the universe? Where did it all come from? Where is it all going? Have no final answers yet. Perhaps they never will. But the search for understanding is itself meaningful, connecting us to the cosmos and to each other across time and space. Tomorrow the sun will rise, and you will continue your journey through this brief moment of cosmic history when stars shine. Life flourishes, and consciousness asks questions about existence. The universe that gave birth to you will continue its expansion, its evolution, its movement toward whatever ending or transformation awaits. Sleep now with the knowledge that you are made of stardust, that your atoms have traveled billions of years to take their current form in your body. You are the universe contemplating itself, a temporary pattern of matter and energy capable of understanding, if imperfectly, the grand cosmic story. The edge of the universe is not a wall but a horizon, always receding, always inviting us to look farther, think deeper, imagine more boldly. What lies beyond that edge, we may never know with certainty, but the quest to understand, to push against the boundaries of knowledge, to ask impossible questions and seek answers anyway, this is part of what makes us human. The silence of deep space surrounds us now as we continue our gentle exploration. Let us drift further into the profound questions that emerge when we contemplate the ultimate nature of reality itself, questions that bridge science and philosophy, observation and imagination. The universe stretches before us, vast beyond comprehension, yet perhaps not infinite, perhaps bounded in ways we struggle to understand, or perhaps truly endless, extending forever in all directions, containing infinite copies of ourselves, pondering these same questions in distant regions beyond any possible contact. What does infinity truly mean in the context of the cosmos? Mathematicians speak of different types of infinity, some larger than others in a precise technical sense. The set of counting numbers, 1, 2, 3, and so on, is infinite. Yet the set of real numbers between 0 and 1 is also infinite and provably larger. Infinity comes in degrees, hierarchies, levels of endlessness that challenge intuition. The universe might be spatially infinite, extending forever without boundary or edge. In such a universe, every possible arrangement of matter occurs somewhere, infinitely often. There would be infinite copies of Earth, of you, of this moment, scattered throughout endless space. Most would differ in small details, but some would be identical down to the quantum level. This seems paradoxical, even disturbing. How can there be infinite versions of you? Yet if space truly extends infinitely and matter is distributed throughout, probability demands it. Given infinite chances, even incredibly unlikely configurations must occur, not just once but infinitely many times. The mathematics is rigorous, even if the conclusion feels impossible. Alternatively, the universe might be finite but unbounded, curved back on itself like the surface of a sphere. An ant walking on a balloon travels a finite distance to return to its starting point, yet encounters no edge or boundary. Three-dimensional space might similarly curve through a higher dimension, allowing the universe to be finite in volume while having no border. In such a closed universe, traveling far enough in any direction eventually returns you to your starting point. Light from the Big Bang might have circled the universe multiple times, arriving from multiple directions. We might see the same distant galaxies in different parts of the sky, their light having taken different paths around the cosmic topology. Current observations suggest the universe is very close to flat, neither strongly curved inward nor outward. This flatness is itself puzzling, a kind of cosmic coincidence that inflation was invented to explain. A flat universe can be either infinite or finite depending on its global topology, possibilities that observations have not yet distinguished. The shape and size of the universe connect to its fate. An infinite flat universe expanding forever will cool toward absolute zero, stars dying one by one, until only cold remnants drift through the dark. A finite closed universe might eventually recollapse, though current observations make this unlikely unless dark energy behaves unexpectedly. These geometric considerations lead to questions about the nature of space itself. Is space a fundamental entity, a stage on which physics plays out? Or is space emergent, arising from more fundamental quantum relationships? Some approaches to quantum gravity suggest that space-time is not fundamental, but rather a useful approximation that breaks down at the smaller scales. In loop quantum gravity, space has a discrete structure composed of quantum units smaller than the Planck length. Space is granular, pixelated at scales far below anything we can observe directly. This discreteness prevents certain mathematical infinities and might explain how the universe bounces rather than hitting a singularity. In string theory, space emerges from the relationships between strings and branes. The dimension of space, its geometry, even its existence depend on how these fundamental objects interact. Space is a derived concept, not a primary one. This suggests that asking about the edge of space, or what lies beyond, might be asking the wrong question, imposing classical concepts where quantum descriptions are needed. Holographic principles suggest an even more radical view. The information content of any region of space might be encoded on its boundary surface, like a hologram storing three-dimensional information in a two-dimensional pattern. The interior volume contains no additional information beyond what is encoded on the surface. In this view, space might be illusory, a projection of information fundamentally residing in fewer dimensions. These ideas connect to the ultimate question: what is the nature of existence itself? Why does the universe exist rather than nothing? This question has puzzled philosophers for millennia and continues to resist easy answers. Some suggest the question is meaningless or based on faulty assumptions about causation and necessity. Others propose that existence is necessary, that nothingness is impossible or unstable. Quantum mechanics allows something to arise from nothing through vacuum fluctuations. If the total energy of the universe is zero, as many cosmologists believe, then creating a universe requires no net input, positive mass energy balances, negative gravitational potential energy, allowing the universe to be a free lunch, in physicist Alan Guth's memorable phrase. But this shifts rather than answers the question: why do the laws of quantum mechanics exist? Why is there a quantum vacuum capable of fluctuating? Why are the laws of physics mathematical, following precise equations that we can discover and understand? These meta-questions probe beyond physics into metaphysics, the study of what must exist for anything to exist. Some physicists and philosophers argue for a mathematical universe hypothesis. In this view, mathematical structures are not just descriptions of reality, but our reality. The universe is a mathematical object, and we are patterns within that mathematics. All consistent mathematical structures exist in a Platonic sense, and we inhabit one that permits conscious observers. This proposal explains the unreasonable effectiveness of mathematics in describing nature. Mathematics works because physical reality is mathematics. The laws of physics are discovered rather than invented, because they are necessary features of the mathematical structure that is our universe. Other mathematical structures correspond to other universes with different laws. The mathematical universe hypothesis faces challenges. Not all mathematical structures permit complexity or consciousness. Most are sterile, too simple to contain observers. Yet in an ensemble of all mathematical structures, it is unsurprising that we find ourselves in one of the rare structures complex enough for life and mind to emerge. Consciousness itself represents a deep mystery in cosmology. The universe evolved for billions of years without conscious observers, yet eventually produced beings capable of understanding it. Matter organized itself into patterns that experience, that feel, that wonder and question. How does consciousness arise from unconscious matter? Why does subjective experience exist at all? These questions belong to the hard problem of consciousness, the challenge of explaining how physical processes give rise to subjective experience. Neuroscience reveals correlations between brain activity and conscious states, but correlation is not explanation. Why does neural activity feel like something rather than being merely information processing without inner experience? Some propose that consciousness is fundamental, not emergent. In panpsychist views, all matter possesses some primitive form of consciousness or experience. Complex consciousness like ours emerges from combinations of simpler conscious entities, much as complex chemistry emerges from combinations of atoms. The universe has a mental aspect throughout, though only in complex structures like brains does this become sophisticated. Others suggest consciousness is an illusion, that what we call subjective experience is simply certain types of information processing. There is no hard problem, because there is nothing to explain beyond the functional organization of the brain. This view struggles to account for the undeniable fact that experience feels real, that there is something it is like to be you. The connection between consciousness and cosmology becomes especially intriguing in quantum mechanics. Some interpretations suggest that consciousness plays a role in collapsing wave functions, turning quantum possibilities into definite outcomes. In these views, observers are not passive witnesses, but active participants in creating reality. The participatory universe concept, developed by physicist John Wheeler, proposes that observers bring the universe into existence through observation. The early universe existed in quantum superposition until consciousness evolved and retrospectively solidified cosmic history through observation. This sounds circular. Observers creating the universe that created observers. Yet it follows from taking quantum mechanics seriously. Most physicists find participatory anthropic principles too radical, preferring interpretations where consciousness plays no special role. Yet the measurement problem in quantum mechanics remains unsolved. What counts as a measurement? Does consciousness matter, or do any interactions suffice to produce definite outcomes? These questions remain debated nearly a century after quantum mechanics was formulated. The role of information in physics has become increasingly central. John Wheeler coined the phrase "it from bit," suggesting that physical reality derives from information. Every particle, every field, every property reduces ultimately to information, to bits of data that could be stored and processed. The universe is a computer, or perhaps computation itself, running a program we experience as physical law. Information cannot be destroyed. According to quantum mechanics and the laws of black hole thermodynamics, when something falls into a black hole, the information it carries is not lost, but encoded in the black hole's event horizon. When the black hole evaporates through Hawking radiation, that information must somehow be preserved in the radiation, though exactly how remains mysterious. This information paradox has driven decades of research into quantum gravity. Solutions propose that information is encoded in subtle correlations in Hawking radiation, or that it is transferred to a baby universe budding off from the black hole interior, or that it escapes through wormholes connecting the black hole to distant regions. Each solution has challenges, and consensus remains elusive. The preservation of information connects to the arrow of time, the fact that time has a direction. We remember the past but not the future. Eggs break but do not spontaneously reassemble. Entropy increases, systems become more disordered. Yet the fundamental laws of physics are time-symmetric, working equally well forward or backward. The arrow of time emerges from statistical mechanics and the universe's initial conditions. The early universe had extremely low entropy, highly ordered compared to later states. As the universe evolved, entropy increased, and this increase defines time's direction. We call the low entropy direction past and the high entropy direction future. But why did the universe begin in a low entropy state? This remains unexplained. Inflation provides a mechanism for smoothing the universe and establishing initial conditions. But why did inflation occur? What set up the conditions for inflation? Each answer raises new questions, pushing the mystery back without fully resolving it. Some cosmologists propose that the arrow of time reverses at the big crunch in cyclic models. As the universe collapses, entropy might decrease, time running backward from the perspective of expanding phases. Observers in each phase would perceive time flowing forward, but external perspectives might see oscillating time direction. this remains speculative and difficult to formalize mathematically. The nature of time itself grows uncertain at the extremes of cosmology. Near the Big Bang or inside black holes, time becomes space-like and space becomes time-like. The roles of time and space interchange. Asking what happened before the Big Bang might be like asking what is north of the North Pole, a question that assumes a structure that does not exist. Eternalism. The philosophical view that all moments of time exist equally finds support from relativity. In space-time diagrams, past, present, and future all exist as different regions of a four-dimensional structure. The flow of time is an illusion arising from our perspective as beings moving through space-time. The entire history of the universe, from Big Bang to ultimate end, exists as a single, unchanging four-dimensional object. This block universe view conflicts with our lived experience of time flowing, of the present moment being special, of the future being open and undetermined. Reconciling physics' timeless picture with our time-bound experience remains philosophically challenging. Perhaps consciousness introduces something beyond the physical, or perhaps our intuitions about time are simply wrong. Alternatively, presentism holds that only the present moment exists. Past moments have ceased to exist, and future moments do not yet exist. This aligns better with experience, but struggles with relativity, which shows that simultaneity is relative. Different observers disagree about which events are happening now, making it unclear what the present moment means in an absolute sense. These deep questions about time, consciousness, information, and existence interweave throughout cosmology. Understanding the universe's ultimate fate requires understanding time's nature. Explaining cosmic origins demands accounting for existence itself. Interpreting quantum mechanics affects predictions about the multiverse. Everything connects. As we float here at the boundary of knowledge, the universe reveals itself as far stranger than our ancestors imagined. Matter and energy are convertible forms of the same thing. Space and time merge into space-time. Certainty gives way to quantum probability. Causation becomes murky near horizons and singularities. The observer cannot be separated from the observed. Yet within this strangeness, patterns emerge. Symmetries constrain what can happen. Conservation laws govern transformations. Mathematics describes it all with remarkable precision. The universe follows rules, even if those rules permit radical possibilities like multiverses, time travel, and spontaneous creation from nothing. Science reveals a cosmos of extraordinary depth and subtlety. Every answer raises new questions. Every mystery solved exposes deeper mysteries. The frontier of knowledge expands, but the unknown expands faster. The more we learn, the more we realize how much we do not know. This should not discourage, but inspire. We live in an age when humans can seriously contemplate questions about the universe's origin, fate, and ultimate nature. We have developed mathematics and instruments that let us peer across billions of light years and back through billions of years. We have discovered that we are made of materials forged in stellar furnaces, and that we inhabit a universe far larger and older than Earth. Our descendants, if any survive the incomprehensible spans of time we have discussed, will know more. They might confirm or refute the multiverse. They might develop quantum gravity and resolve the information paradox. They might understand consciousness and its role in nature, or they might encounter new mysteries we cannot yet imagine, questions we lack the concepts to formulate. The search for understanding is endless, because the universe's richness exceeds any finite mind's capacity to fully grasp it. Yet the search is not futile. Each generation adds to human knowledge, building on what came before. We stand on the shoulders of giants, as Newton said, seeing farther because of those who came before us, and we become giants for those who follow, if anyone follows. Our observations, our theories, our questions become part of the heritage passed forward. The cosmic story we have explored tonight, from quantum foam to infinite multiverse, from the first moments after the Big Bang to the last black hole's evaporation, represents humanity's current best understanding, subject to revision but genuine progress toward truth. Sleep now with these vast thoughts as gentle companions. Let the mystery of existence lull you into rest. You need not understand everything to be part of it. You are a child of the cosmos, brief as a spark, yet connected to eternity through the atoms you borrow and return. The universe cradles you in darkness punctuated by starlight, in silence broken by the whisper of cosmic expansion, in cold warmed by the nuclear fires of distant suns. You belong here, improbable yet actual, temporary yet meaningful, small yet capable of grasping the infinite. Tomorrow awaits with its ordinary miracles, the sunrise that has happened billions of times yet remains new, the breath drawn into lungs built from cosmic debris, the thoughts firing across neural networks more complex than all the stars visible to the naked eye. You will wake to continue your journey through this moment of cosmic history when wonder is possible. For now, release your questions. Let go of the need to know what lies beyond the edge. Accept the mystery with gratitude that mystery exists to contemplate. The universe keeps its deepest secrets, and that is gift enough, for it means the story never ends. Discovery never ceases. Wonder never exhausts itself. In the deepest darkness of space, where even the faint glow of distant galaxies fades to nothing, we find ourselves confronting the void. Not emptiness, for even empty space contains quantum fields, virtual particles, dark energy, but the void of unknowing, the boundary where knowledge ends and speculation begins. What can we truly say about the ultimate fate of everything? We have explored heat death, the slow cooling of an eternally expanding universe until all stars fade, all black holes evaporate, all structure dissolves into a thin soup of particles spreading through infinite space. This ending is not dramatic, but gradual, a fading rather than a finale. In this far future, after 10 to the 100 power years have passed, the universe will be unrecognizably different from today. No stars will shine, no galaxies will spin. The cosmic microwave background will have been stretched to wavelengths longer than the observable universe itself, its photons so dispersed that encountering even one becomes unlikely. The temperature everywhere will approach absolute zero, that theoretical limit where all thermal motion ceases. Yet even at these incomprehensibly low temperatures, quantum mechanics prevents complete stillness. Zero-point energy ensures that some motion persists, an irreducible quantum jitter that can never be eliminated. Matter itself may cease to exist if protons decay. The stability of protons remains uncertain. No experiment has ever observed a proton spontaneously decaying, but theories suggest it must eventually happen. If the proton lifetime is 10 to the 40 power years or longer, then even after all stars have died, proton decay will continue reshaping the remnants. White dwarfs, those cooling stellar cores, will slowly dissolve as their constituent protons decay. Each decay releases a tiny flash of energy, briefly warming the surrounding space by an infinitesimal amount. Over time, measured in numbers too large to name easily, every white dwarf will fade completely, transforming into diffuse radiation. Black holes present a different fate. These objects, formed from collapsed stars or present at galaxy centers, will persist long after ordinary matter has decayed. A black hole with the mass of our Sun would take approximately 10 to the 67 power years to evaporate through Hawking radiation. Supermassive black holes would last even longer, their lifetimes extending to 10 to the 100 power years or beyond. Yet even these ultimate survivors must eventually fade. Hawking radiation, though incredibly slow for large black holes, never ceases. Photons and particles trickle away, carrying mass energy from the black hole into the surrounding space. The process accelerates as the black hole shrinks, with the final moments releasing a burst of high-energy radiation. When the last black hole evaporates, perhaps 10 to the 106 power years after the Big Bang, the universe will have reached a new state. No stars, no planets, no black holes, no complex structures of any kind. Only a cold, thin gas of photons, neutrinos, electrons, and positrons, spreading ever farther apart as space expands. Is this truly the end? In one sense, yes. Nothing interesting can happen anymore. The universe has reached thermal equilibrium, maximum entropy, the heat death long predicted by thermodynamics. Time loses meaning because nothing changes. Every region looks like every other region, all cold, all dark, all empty. Yet in another sense, the story might continue. Even in this seemingly dead universe, quantum fluctuations persist. Over timescales that make the age of black hole evaporation seem brief, random fluctuations might assemble complex structures by pure chance. A Boltzmann brain, a spontaneously formed conscious entity, might flicker into existence for a brief moment before dissolving back into chaos. These random fluctuations represent a strange kind of immortality for complexity. Given infinite time, even incredibly unlikely events must eventually occur. A perfect copy of you, assembled atom by atom through random chance, will appear somewhere, sometime. Not just once, but infinitely many times if the universe truly expands forever. This raises disturbing philosophical questions. If most observers in the far future are Boltzmann brains, random fluctuations rather than products of evolution, why are we not Boltzmann brains? The fact that we have consistent memories and exist in an ordered universe suggests something is wrong with this picture. Perhaps the universe does not expand forever, or perhaps our understanding of probability in infinite universes is flawed. Some cosmologists take this as evidence against eternal heat death. If a theory predicts that most observers should be random fluctuations, and we are clearly not, then perhaps the theory is wrong. This reasoning has motivated alternative models where the universe does not expand forever, or where new physics intervenes to prevent eternal heat death. The Big Rip scenario offers a more dramatic ending. If dark energy strengthens over time rather than remaining constant, the universe's expansion will accelerate without bound. Eventually, the expansion rate becomes so extreme that it overpowers all forces holding structures together. First, galaxy clusters dissolve as space between galaxies expands faster than gravity can pull them together. Then individual galaxies are torn apart, stars ripped away from their galactic centers. Solar systems disintegrate as planets are torn from their orbits. Then stars themselves are shredded as expanding space overcomes the gravity holding them together. Molecules break apart as chemical bonds cannot withstand the accelerating expansion. Atoms are ionized as electrons are torn away from nuclei. Finally, atomic nuclei themselves are ripped apart. Protons and neutrons shredded into their constituent quarks. The universe ends not in cold silence, but in a cataclysm that destroys everything. The Big Rip would occur at a specific moment, perhaps 50 billion years in the future, perhaps longer. The exact timing depends on how quickly dark energy strengthens. Current observations suggest dark energy remains constant, making the Big Rip unlikely. But we have only observed dark energy's behavior over a small fraction of cosmic history. It could begin strengthening in the future. Vacuum decay presents perhaps the most unsettling possible ending. If our universe exists in a false vacuum state, a quantum tunneling event could trigger a transition to the true vacuum. A bubble of true vacuum would form somewhere in space and expand at light speed, destroying everything it touches. The bubble wall would arrive without warning, traveling at the speed of light. Inside the bubble, physical laws would be completely different. The fundamental constants that govern our universe, determining atomic structure, chemical bonds, stellar evolution, everything we know, would have different values, or might not exist at all. Most calculations suggest that the true vacuum, if it exists, would not support the existence of atoms. The electromagnetic force might be much stronger or weaker, preventing electron orbitals from forming. The strong nuclear force might be too weak to hold atomic nuclei together. Complex chemistry would be impossible, and life, as we understand it, could not exist. This ending would be absolute. Unlike heat death, where structures dissolve but particles remain, vacuum decay would erase everything and replace it with a universe utterly unlike our own. No remnant of our universe's history would survive. Everything that ever existed, every thought, every creation, every trace of our existence would be obliterated and overwritten with alien physics. The universe might already be undergoing vacuum decay somewhere beyond our horizon. A bubble could be expanding toward us right now, and we would have no way to detect it until the moment it arrives. This possibility has inspired science fiction scenarios, but also genuine scientific concern about experiments that might trigger vacuum decay. When physicists propose building increasingly powerful particle accelerators, some worried that high-energy collisions might create conditions that trigger a transition to true vacuum. Calculations showed that cosmic rays naturally produce collisions far more energetic than any accelerator, and the universe has survived billions of years of cosmic ray impacts. If vacuum decay were easy to trigger, it would have happened long ago. Still, the possibility cannot be entirely dismissed. We might live in a metastable vacuum with an extremely long expected lifetime, vastly longer than the current age of the universe, but not infinite. Sometime in the far future, perhaps after all stars have died and all black holes evaporated, a quantum fluctuation might finally trigger the transition, or perhaps not. Perhaps our vacuum is truly stable, the lowest possible energy state, safe from decay. Measurements of particle physics parameters, particularly the Higgs boson and top quark masses, allow calculations of vacuum stability. Current results place us tantalizingly close to the boundary between stability and metastability, with large uncertainties preventing definitive conclusions. Beyond these physical endings, some theories propose more exotic fates. If extra dimensions exist, our three-dimensional brain might collide with another brain, triggering a catastrophic release of energy, or our brain might be absorbed into a higher dimensional bulk, causing the three-dimensional universe we inhabit to simply cease existing. Some speculative theories suggest that the laws of physics themselves might evolve or change over cosmic timescales. If physical constants are not truly constant but drift slowly, the universe's ultimate fate might be impossible to predict because the rules will be different in the far future. Loop quantum cosmology proposes that when the universe approaches maximum entropy and minimum temperature, quantum gravitational effects might cause another bounce. The dying universe would transition into a new expanding phase, reborn from its own ashes. This provides a natural mechanism for eternal recurrence without requiring a big crunch. String theory's landscape of possible vacuum states suggests that our universe might transition between different vacua even without reaching true vacuum. These transitions would change the laws of physics, but might occur smoothly rather than catastrophically. The universe could age and transform, evolving through different physical regimes over its eternal existence. What role does consciousness play in all this? If the universe ends in heat death or vacuum decay, does that mean consciousness ends absolutely? Or might consciousness persist or re-emerge in some form? These questions venture beyond current physics into metaphysics and philosophy. Some philosophical traditions propose that consciousness is fundamental and cannot be destroyed. Physical forms come and go, but awareness itself persists, taking new forms as conditions allow. Modern physics neither confirms nor refutes such ideas, operating within a framework where consciousness is not treated as a fundamental entity. Yet consciousness poses genuine puzzles. The hard problem of consciousness, explaining how subjective experience arises from physical processes, remains unsolved. We do not understand why there is something it is like to be conscious, rather than neural activity occurring without inner experience. This gap in understanding leaves room for possibilities beyond physicalist reductions. If consciousness is an emergent property of complex information processing, then it depends on suitable physical structures. When the universe reaches heat death and no complex structures can form, consciousness would cease. It might re-emerge briefly in Boltzmann brain fluctuations, but would have no continuity or development. If consciousness is more fundamental, the universe's physical fate might not determine consciousness's ultimate fate. Awareness might transition to different substrates as physical conditions change, or it might exist independently of physical instantiation. These ideas remain speculative, impossible to test with current methods. The question of meaning emerges inevitably from contemplating cosmic endings. If the universe will eventually die, does anything we do matter? If all stars will fade and all structures dissolve, what is the point of existence? These questions have troubled philosophers and inspired theologians throughout history. One response is to find meaning in the present moment rather than in eternal persistence. A beautiful sunset has value, even though it lasts only minutes. A human life has meaning even though it spans only decades. The universe might have meaning, even if it lasts only trillions of years rather than forever. Another response emphasizes the improbability and preciousness of our existence. In a universe heading toward heat death, the current era when stars shine and life exists is special. We inhabit a brief window of cosmic history when complexity is possible. This makes our existence more precious, not less. Consciousness arising in the universe represents a profound transformation. For billions of years, matter and energy evolved unconsciously, following physical laws without awareness. Then, at least on Earth and possibly on countless other worlds, matter organized itself into patterns capable of experiencing, understanding, and valuing. This emergence of consciousness means the universe can know itself. Through our eyes, the cosmos observes its own grandeur. Through our minds, it contemplates its own mysteries. Through our hearts, it values beauty and meaning. We are the universe's way of experiencing itself. In Carl Sagan's memorable phrase, "Even if consciousness is destined to fade when stars die and complexity becomes impossible, the fact that it existed at all seems meaningful." The universe produced beings capable of asking why they exist, of discovering physical laws, of creating art and music, of loving and hoping and dreaming. These achievements have value even if impermanent. Some find comfort in the idea that our actions ripple forward through time, influencing the future in ways we cannot fully predict. The kindness you show today might inspire someone who inspires someone else. A chain of influence extending far into the future. Your thoughts might contribute to collective human understanding, adding to knowledge that persists beyond your lifetime. Others find meaning in connection, in the web of relationships that link every conscious being to every other. We are isolated individuals in one sense, but in another, we are nodes in a vast network of minds sharing this moment in cosmic history. Our individual endings do not erase the connections we made or the ways we influenced each other. The search for meaning in an ending universe parallels personal searches for meaning in finite lives. We all face our own mortality, the certainty that our individual existence will end. Yet most people find ways to live meaningful lives despite this. We love, create, explore, and grow, finding value in the journey rather than requiring eternal persistence. Perhaps the universe's ending, if it comes, should be viewed similarly. The cosmic story has value not because it lasts forever, but because it contains moments of beauty, complexity, consciousness, and meaning. The stars will fade, but they shone. Life will end, but it existed. Consciousness will cease, but it experienced wonder. The possibility that endings are also beginnings offers another perspective. If the Big Bounce is correct, our universe's death seeds a new universe's birth. If the multiverse exists, new universes constantly emerge even as others age and die. If consciousness is fundamental, it might transition to new forms beyond our current understanding. We stand at a unique vantage point in cosmic history. The universe is old enough for stars to have formed, for heavy elements to have been created, for planets and life to have emerged. Yet it remains young enough that stars still shine, galaxies remain visible, and the cosmic microwave background provides clear evidence of our universe's origins. Future observers, if any exist trillions of years hence, will inhabit a darker, emptier cosmos. They will see fewer stars, no distant galaxies, no cosmic microwave background. Much of the evidence we use to understand cosmology will have faded from view. They might not be able to discover what we have learned about the Big Bang and cosmic evolution. This suggests we are fortunate, living at a time when the universe is maximally knowable. The evidence of cosmic origins remains visible. The structure of the cosmos is accessible to observation. We can study cosmology because the cosmos has not yet aged beyond the point where key evidence disappears. In this sense, conscious beings like us might be rare, not just in space, but also in time. The window when the universe supports complex life while retaining evidence of its own history might be brief compared to cosmic timescales. We exist during this special epoch when both complexity and cosmological discovery are possible. This adds urgency to the scientific enterprise. The knowledge we gain now might not be accessible to future beings. Our observations of distant galaxies, our measurements of the cosmic microwave background, our discoveries about dark energy, these might be unique opportunities that will not come again. We document the universe for any descendants who might arise in darker ages. As we contemplate these vast timescales and ultimate endings, a sense of perspective emerges. Our individual concerns, our daily worries, seem small against the backdrop of cosmic evolution. Yet they are not meaningless. We are part of the story, brief participants in the universe's grand narrative. Every moment of consciousness represents a small victory against entropy, a temporary organization of matter and energy into patterns capable of experience and understanding. Every act of kindness, every discovery, every creation adds to the richness of the cosmic story, even if the contribution is infinitesimally small against the vastness of space and time. The universe will continue on its journey toward whatever ending awaits. Stars will burn their fuel and die. Galaxies will fade as they exhaust material for new star formation. Black holes will slowly evaporate. Space will expand, carrying the remnants of cosmic structure farther and farther apart. The great cosmic clock winds down. Entropy increases. Organization gives way to disorder. Yet even in this darkening future, beauty exists. The final stars will burn with quiet dignity. The last black holes will evaporate in showers of particles and light. The universe's ending, whether through heat death or big rip or vacuum decay or some fate we have not imagined, will be the culmination of a story billions of years in the unfolding. And perhaps, somehow, somewhere, in ways we cannot predict or understand, something new will emerge. Perhaps the ending truly is another beginning. Perhaps consciousness finds ways to persist we cannot imagine. Perhaps the multiverse ensures that even as our universe fades, others flourish. Perhaps the cosmos is more creative, more resilient, more surprising than our best theories suggest. We do not know, cannot know, what ultimately awaits. The edge of the universe, the boundary of the observable cosmos, is also the edge of knowledge. Beyond lies mystery, vast and profound, inviting wonder rather than requiring answers. Sleep now, knowing you have journeyed to the farthest reaches of human understanding. You have contemplated the birth and death of universes, the emergence and fading of consciousness, the ultimate questions of existence and meaning. These thoughts are rare and precious, possible only in minds complex enough to grasp them. Tomorrow you will wake to ordinary miracles, to sunshine and birdsong, to conversation and work, to the simple pleasures and challenges of finite existence. But tonight you have touched infinity, you have pondered eternity, you have asked the questions that separate humans from all other known forms of matter in the universe. Rest now in the mystery, comfortable with not knowing, content to be part of a story whose ending remains unwritten. The universe holds you gently as it holds all things in the great dance of existence that began long before you and will continue long after, but which includes your brief moment as an essential note in the cosmic symphony. Good night, conscious pattern of stardust. Good night, universe reflecting on itself through your awareness. Good night to questions and answers, to knowledge and mystery, to endings and beginnings, to all that is and all that might yet be. Sleep peacefully at the edge of everything, knowing you belong here, knowing your existence matters, knowing that to wonder is enough, that to question is its own answer, that to be aware is the universe's greatest achievement. The cosmos breathes you in and out, And in this breath, this moment, all of existence is contained. Rest now in that truth, simple and profound, final and eternal, ending and beginning, always and forever. Good night.